Hello, folks. Welcome to day two, lesson two on series. So, what we talked about previously is we talked about the divergence test, which is basically looking at the last term and seeing if that last term of a sequence is approaching zero or not. We looked at infinite geometric series and making sure that the R was less than 1. We then also did the p-test again, which I told you we're going to talk a little bit about today, and we did the comparison tests and the limit comparison tests. So today we're going to introduce the three next tests that we're going to use for series that have positive terms. That means all the terms in the sequence are positive, and we're adding up a whole bunch of positive terms. So we're going to talk about the other three tests that we're going to be using to kind of fill out our complete suite of tests. So this first test we're going to talk about is the integral test. And the integral test is effectively saying we can relate a sequence to a function. So we're going to say let a sub n basically be f of n. That's basically saying if you plugged in some integer for n into some function, you would get the actual value of the sequence of that term. And we're going to make sure that we have some couple things that we're going to have to, ooh, this thing slides when I put my hand on it. Okay, so there's a couple conditions that we need. Okay, one condition that we definitely need is f of x must be positive, right? We just talked about how we're doing this for positive terms. And then the other thing that it also has to be decreasing. That means the function is constantly getting smaller as x gets larger, and has to be continuous. And that's because to do integrals, we need continuity. So, and it really has to be decreasing for all, it doesn't have to be for all x, it just has to be once it hits some number, it has to be decreasing. So we'll say it has to be decreasing for all x greater than some value c, okay? So in the event that the function is decreasing and positive and continuous, we kind of know that it's going to be decreasing. It's going to look like this, right? It's going to be going down. It's going to be getting closer and closer to zero. It's not going to hit zero because it has to be positive. So, but it's going to be going down and approaching zero. Okay. So what we know then, and I'm going to talk about why in a second. So then if this is the case, if we can make this situation where the function is decreasing, positive, and continuous, then we're allowed to say the following. We're allowed to say that in the event f of x, I shouldn't have x there. So the integral from c to infinity of f of x and dx will, and the series. So this is where I guess I should use n. So the improper integral, which is what we have here, the improper integral and the infinite series, they will converge or diverge together. So why? Okay, so I started a little display here just to show you why. Now, this is not a formal proof, but this is just kind of like a display on why. So the first left one here is going to assume that we have some function. Notice that it's positive, decreasing, continuous. Both left and the right are positive, so this is kind of f of x here. And it's decreasing. Now, the sequence, right, the sequence basically is saying, hey, let's add up this and this. These are these points, right? That's the sequence. We're adding up these points. So basically, if I want to say, let's think about the area under this curve. If we thought about the area under this curve, which is a little hard to see, but the area under this curve, right? That's this improper integral. All this area under this curve, okay? And if we know this converges, that means it's bounded. That means it's approaching some number because we're assuming the integral converges. Now, if we also say, well, let's add up this sum. Well, if I want to add up these green little dots, I could display these green little dots instead as green little dots as rectangles. Well, why? Well, if the width here is 1, I can basically say, see this guy right here? That is the same area as the value of that green dot because the width is 1. So I can depict each one of these as rectangles. And it keeps on going, right? It keeps on going and going and going. And if I know that this yellow stuff, right, the yellow area converges, and I know that the purple, which is effectively the sequence, right? The purple, the sum of the rectangles. Because each rectangle, I mean, we call this A1, right? If this is A1, this rectangle is A1, right? If we call this value here A2, this rectangle is A2. So the sum of the rectangles, right? The sum of the rectangles must be less than this area under the curve. So therefore, if the area under the red curve converges, so must the area of the rectangles. And now, vice versa, we could do the same thing over here. Again, we have this area, and we know this diverges. Okay, this is going to infinity. This is getting really, 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 really big, right? It's not getting to some number that we can see. It's going to keep on growing and growing. Now, if I say, well, what about this rectangle here? Well, instead of just going to the left, I'm going to depict this rectangle as saying there. Oh, I'll just draw it to the right instead. And the only reason why I'm doing is because I know it's diverging. I know the red curve is diverging, and I just want to show that the area now under these green rectangles is also going to diverge, because in this case, I'm using the rectangles to the right. And since they're over, they will also diverge. So you may ask, well, why did you use the rectangles to the left on the left graph, and why did you use the rectangles to the right on the right graph? Well, because on the right, I'm trying to prove divergence, right? So I'm trying to show, hey, the red curve diverges, so I'm going to show something is bigger than something that's diverging, right? On the left curve, I'm trying to show convergence. So I'm trying to show the fact that the area is something that is smaller than something that is converging. If I decided to use the areas, the left rectangles on the right, I wouldn't prove anything, right? I wouldn't be able to prove the fact that I'm greater than, even though those areas would also diverge and they'd also be going to infinity. I wouldn't be able to prove it because I'm not showing the fact that they're greater. Okay, so that was a long-winded explanation why. Now, if I come back to here, one of the things that we can use is that we can talk about the fact that now we know one of the most important sequences. This is one of the most important sequences. And we can talk about this. Now, if we know the p-test, we know what this does, right? But this is something that we would use the integral test to prove, right? We could say, well, therefore, we could compare this to that. And we did our improper integrals before, so this is nothing new. And we could evaluate it. And we know that goes to infinity because the ln of infinity is infinity. So therefore, we know this diverges. And that's the proof that this sequence here, by the integral test, also diverges. This sequence here is a very famous one. If you think about it, it's this. It's a famous sequence, and it does diverge, even though it's getting closer to zero. People think, hey, look, it's getting smaller and smaller and smaller. It looks like it's going to converge to some number, but it doesn't. And this is called the harmonic series. The harmonic series actually diverges. And there's your proof using the integral test. Okay, next, the ratio test. So when we're thinking about the ratio test, the thing that we want to kind of think about is what's happening between subsequent terms. You have one term, then you have the next term, then you have the next term, and the next term. And every single time they're getting kind of smaller and smaller, hopefully, because you want them getting smaller and smaller and smaller and closer and closer and closer to zero. Now, we've been assuming that all positive terms, and that's fine. We can continue to use positive terms, but we're also going to be able to use this in the future too. So that's why you're going to see me use some absolute value symbols, which aren't really necessary now, but they would be necessary later. So if you're wondering why those symbols are there, that's the reason why. Okay, so the idea is that we're going to be thinking about, you have these terms, right? You have a sub 1, a sub 2, a sub 3, dot, 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 a sub n plus 1, and they keep on going. And what we're going to be looking at is the ratio between terms. So what we're going to be looking at is this ratio right here. And that's effectively the ratio between some term in the future, a sub n plus 1, and the term that was right in front of it, a sub n. And we're going to look at the absolute value of that ratio. And again, if both terms are positive, we don't need it. But the idea is, in the distant future, what is this ratio going to look like? Okay, this ratio is going to be, hopefully, get a small number, right? Because if it's small, which means the top one is smaller than the bottom one, that means that it's getting closer and closer to 0. So we're going to look at what happens in the distant future to this ratio. And this ratio we're going to call rho. And this rho basically is some number that hopefully we're going to say, hey, this ratio is approaching something in the future. And the idea is, if we look at this and we say, okay, well, what is rho going to be? If rho is greater than 1, that means the top one is getting bigger than the bottom one. That's not so good, right? If the top one is bigger than the bottom one, we're going to have a divergent series. If it's less than 1, guess what? Yep, it converges. And lastly, if it equals 1, you know nothing. And I write this down because people think, oh, wow, I did something. But you know nothing. If you get rho equals 1, go back to the drawing board. It's like, great, you just did a great limit. You just figured out it equals 1. And now you need to go back and do something else because it doesn't tell you anything. Okay, 1 tells you nothing. It doesn't tell you convergence. It doesn't tell you divergence. You can get 1 and have it converge. You can get 1 and have it diverge. You really don't know anything if you get a rho equals 1. You go back and use a different test. I think the best kind of thing to show here would be an example of a problem where you would use this. Now, your instincts might be clear on this, but the ratio test really helps. So let me give you something like this. We'll have n cubed over e to the n. Okay, so you look at this and you're like, okay, wow, n cubed over e to the n. E to the n is going to be getting to infinity a lot faster than n cubed. Your instincts should be saying this thing's probably going to converge. But if we now think about the ratio, let's think about the distant future, what this is going to look like in the way, way distant future. Let's think about the term n plus 1. So the n plus 1 term is going to be this, n plus 1 cubed over e to the n plus 1. And that's going to be over a sub n. See, and remember, the whole question that we're asking, right, is, does this diverge or converge, right? So if a sub n, this is a sub n, right? This is here is the expression for a sub n. So we just took that expression, we put it in the denominator, and then we took the same expression, but we figured out the next one, kind of n plus 1, and we put that in the numerator. Now, if we start evaluating this, I'll take the time to do it stepwise in the beginning. I don't usually, once we get going, we don't need to kind of spend all this time. Voila. Okay, so we know that this limit here, what's n cubed over n cubed, right? And when the same degrees in the numerator and the denominator, n cubed plus 3n squared plus 3n plus 1, but we really care about that, right? All we really care about is the n cubed here, if we expand this, and the n cubed here, because they're the highest degree here. So we know that this here is going to approach 1. So the limit of this is going to approach 1. What's this going to approach, right? So the limit of this is going to approach 1. And this is going to be, well, we know our exponent rules, right? This is going to be 1 over e. So this is going to be, whole thing is going to be 1 over e. So now let's circle back. 1 over e. Well, e is 2.7 something, something, something. It's bigger than 1. So we know that this fraction is less than 1. So if we know rho is less than 1, what does our ratio test tell you? Oh, it tells you that the series converges. And the series converges by the ratio test. Last test, the test you're going to use the least, but we're going to talk about it briefly. The root test. And the root test says, again, you have some, again, we're talking about some series here. And this is really useful for when you have something to the power of n and you want to be able to evaluate it. And what the root test says, it's similar to a rho thing, but what it says that if you do the limit as n goes to infinity, and I'm putting an absolute value here, The only reason why I'm putting an absolute value there, folks, is because in the event that there's a negative in the future. Right now we're dealing with positives, but in the future we'll have some negative terms. So the nth, we're taking basically the nth root. We're taking the nth root of this expression, of this series. And we're going to say the nth root of this is some rho. And we're going to use the same exact rules. If rho, and the good thing is that it's very similar, right? If this diverges, if rho is less than 1, it converges. It's just like the ratio test. And if rho equals 1, you know nothing. I guess it's important to say if rho is approaching infinity, then it also diverges. I mean, it's kind of important. That's also the nth root test. It's also the divergent test. If this is approaching infinity, then it's not, the actual expression is not approaching 0 anyway. So you could have used just the divergence test instead. Okay, so what does that look like? Well, you could have a series like this, which gets kind of fun, I guess. You could have something that looks like, we'll choose a 4. Why not? It really doesn't matter. Any number there. And you could have any expression in here. And you could say, well, I wonder what this does. That looks fun. So you look at that and you say, wow, I have no idea if that's going to get big or small. This guy right here is getting really large, right? I mean, that tells you, wow, this thing is getting big. It's getting big fast. So part of you is saying, wow, if this is getting big so fast, it's got to diverge, right? But don't trust that instinct, because you also have n's in here too. And the n's in here are going to be working with that n, and you got to kind of figure out what's going to happen, because if you take a small number here to some big power, it actually approaches 0, right? So that's what we're doing here. Don't trust this alone. Don't say, hey, don't just look at the n, okay? So what we're going to say is that we're going to use the root test now. We're going to come back and say, let's figure out what is the limit as n approaches infinity, the nth root of n cubed minus n over 3n cubed plus 2n squared. Now, why are we using the nth root test? Because of this n, right? This n here is telling us to use the nth root test, because that basically turns into the kind of limit problem that you would have loved to have seen last year, that you really hope would have been on a test, because it would have been a walk in the park. 1/3, right? Highest degree is 3 and 3. 1/3, less than 1. Therefore, the series converges. That looks like a D, so I'm going to change that. Because we have the rho is less than 1 by the root test, the series converges. Okay, so there are your 3 tests that we're going to talk about. Go ahead and tackle assignment 2 now. Look for my notes on what I want you to do on assignment 2. And then we're not going to do number 2 yet until I give you some more conversation about what you need to do for intervals of convergence. Talk to you soon.